Thank you very much. Thank you very much. My talk is going to be about the behind the pixels of the facial recognition, and it's going to all about Python and real world implementation. But let me introduce myself first. This is Sefik. I have been working as a software engineer since 2010, and currently I'm working London-based telecommunication company, Verbos. We are trying to build and deliver better connection for London commercials. But for today, I'm here because I'm the creator of DeepFace library for Python. Meanwhile, I have a personal blog, which is my name plus first letter of my surname, sefix.com. Meanwhile, I have a YouTube channel with same name. And finally, that's my Twitter account. We are planning to have 35 minutes talk and 5 minutes questions. But meanwhile, if you have any questions, if you mention me in Twitter, I promise I will respond. But before we begin, I want to ask a question to you. I wonder how many of people are using Apple Wallet or Google Pay in daily shoppings. Would you please answer up? It's quite a lot. How many of people are using Face ID technology or face recognition technology during the shopping? Or almost same. It's quite a lot, and this is really showing facial recognition are the reality of today. It's much safer than people confirmation. I'm going to show it because according to Apple's security report published in recent years, they declared that Face ID technology is 20 times safer than Touch ID. I mean, false positive attempt possibility with Touch ID is 1 in 50K. On the other hand, false positive login possibility with Face ID is 1 in 1 million. This is much lower when you go to bank branch, for example. That's why nowadays all banks are allowing Face ID technology to authorize you. I need to explain this because this may cause a lot of confusion. When I say I'm the creator of the DeepFace library, many people are asking me about, are you using at Meta, are you using at Facebook? The answer is no, because they are right. Facebook developed a DeepFace model, and you can see its research paper on the left-hand side, and its name of that paper, DeepFace, Closing the Gap to Human Level Performance in Face Recognition, Face Verification. And it's basically a convolutional neural networks model. You can see the model in the left-hand side. Even though Meta published the model structure, the backbone of that model, they did not publish the pre-trained weights of that model. So you cannot use that model publicly. In some open source implementations, some open source contributors are using that backbone and train that model with open source datasets. By the way, Facebook used their own dataset, not published publicly, to train that model. So the accuracies got from the open source implementations are much lower than the declared score of that paper. In the middle column, DeepFace library, you can see its logo. I'm going to talk about that DeepFace library for Python. And finally, it's very common nowadays, DeepFace Lab. It's a deepfake application, but DeepFace Lab, it's a tool to create deep fakes. So I'm not going to talk about the DeepFace model directly. I'm not going to talk about the deepfake. The talk is mainly based on DeepFace library for Python. And these are some numbers of DeepFace library. Currently, it passed 10K stars on GitHub. and it's available on Python package index, PyPy or pip, and it got over 2 million installations on Python package index. Meanwhile, we published 3 different academic papers, peer-reviewed papers, and those got more than 500 citations in academic papers. Its source code is available publicly in that URL address. Also, nowadays in London streets, you can see those things, live facial recognition in operation, and you can see CCTVs are everywhere. This may make you feel like you're living in George Orwell's 1984, or Big Brother is watching you. But reality is a little bit different, because I got this news from BBC, and still in 2024, war crimes are happening. And as you can see, soldiers seen killing unarmed civilians, and you can find the related news from BBC I shared. Meanwhile, a hacker group, you can access their study from the URL I shared behind. Use DeepFace library because it's publicly available. It's licensed under MIT, and with DeepFace technology, they can identify some war criminals. And I did not do that study. The hacker group just emailed me and informed me, and it's really an important milestone for me. It makes me feel different, not happy. But the reality is this. DeepFace and other open source tools are democratizing AI. Otherwise, governments can have millions of CCTVs. They can run facial recognition, but in that way, it's going to be advantages for us. I'm going to talk about the background of facial recognition technology, and it's consisting of a pipeline, and that pipeline consists of 4 common stages. That's a modern facial recognition pipeline. I'm not going to deep dive, but basically, when you feed a facial image, you are going to detect the facial area of that image. Thereafter, you are going to align that image according to its positions of eyes. Here, I fit an image pair because I'm going to ask this face pair is same person or different person. Early stages are detection and alignment, and the most important stage is representation. Here I mentioned Facebook's DeepFace model is a model. It's a CNN-based model, and we know its backbone, even though we don't know its pre-trained weights. Here, VGG face model is represented, and its expected input size is 2 to 4 times 2 to 4. Once we detect and align the facial area of the given images, we resize that image to that expected size. Thereafter, we fit those facial images to those pre-trained models. And for example, VGG face is developed by Oxford University's researchers, and VGG is referring to Visual Geometry Group. And you can consume this model from DeepFace with a line of code. I'm going to emphasize it. When you feed facial images to those CNN models, you are going to have multi-dimensional vectors at the end of the model, its output layer. Normally, if you are familiar with machine learning projects, and if you are running classification tasks, if you have many outputs in the output layer, you normally focus on the most dominant output of the output layer. and that's going to be your classification prediction. But in facial recognition models, all outputs are important, and we are using those outputs as vector embeddings. This approach is currently being used in image recognition or LLM models. Nowadays, when you ask a prompt to ChatGPT, actually it transforms it to a vector embedding similar to here. They may not use a CNN model in the background. Most probably they are using a LSTM model to represent sentences to vector embeddings, but logic is same. You are using a deep neural networks model. You are giving an input. It can be anything, and the result is vector embedding. Thereafter, we fed two facial images, and at the end of the representation layer, we have two different vector embeddings. And in VGG face model, we are getting 4096 dimensional vectors in output layer. But this is not important. For example, FaceNet model generates 128 dimensional vectors. It's not important. And in the last layer is responsible for verification. We are basically using high school formulas to find the distances between those vector embeddings. For example, you can use Euclidean distance, L2 normalized Euclidean or cosine similarity. Here D refers to distance formula you are using. Once you feed those embeddings to that distance formula, you are getting a scalar value. I mean a float number. Thereafter, you need to compare this float number to this scalar value to a threshold, because we expect that distance coming from same person should have low distance. Distance coming from different persons should have higher values. And this threshold is tuned already. I mean, you can find the pre-tuned threshold value for VGG face model in DeepFace if you wonder. And once you compare that distance and threshold value, you are going to find this pair is same person or not. This is the background of a facial recognition pipeline, but to be honest, you don't you don't have to know this flow at all. You should just know this when you feed a facial image. Facial recognition models are responsible for generating embedding, and those embeddings are not meaningful for people. And in other words, computers can see your face like these embeddings. Here I'm going to start to talk about DeepFace. And DeepFace is like a automatic car. And all you need to do is import DeepFace if you install it already from Python package index. As from DeepFace, import DeepFace. Thereafter, we are going to call its verification function, and all you need is to feed exact image paths of face pair. Thereafter, this is going to return a dictionary, and we are going to check its verified key. If it's true, this means this image1.jpg and image2.jpg image pair is same person. Otherwise, they are different persons. Like automatic car, you just need to call verify function. You don't care about anything. But if you like to use manual car, DeepFace has that option too. Because in the background, it wraps 10 different facial recognition models in the first illustration. These are VGG face, FaceNet, OpenFace, DLeap. You can see DeepFace model from Meta, but this is using the backbone of Meta's DeepFace model, but its pre-trained weights are retrieved from an open source implementation, but its accuracy score is much lower than the declared score. ArcFace, DeepID, SFace, and finally GhostFaceNet. If you don't mention anything, I mean, if you call just verify function and pass image pair, it's using VGG face, but you can switch to any other facial recognition model. Similarly, as you may remember, early stages are consisting of detection and alignment. And the default face detector model in DeepFace is OpenCV. If you don't mention anything, it's going to use OpenCV model, but you can switch it to SSD, MTCNN, DLIP, 10 different face detectors. Default distance metric is cosine, but you can switch it to Euclidean. And finally, default alignment mode is enabled, but you can disable that mode too. As you can see, there are many configurations, and we can customize the facial recognition pipeline as coded here. When we are calling verify function, we can set the model name, and model name can be one of this model names list, or detector backend can be set from these detector backends. Distance metrics can be set from this 3 distance metrics, and you can enable or disable alignment modes. But you don't have to set the model name, detector backend, distance metric, or alignment. These are optional fields. We recently published an academic paper in Journal of Information Technologies, and the title of the paper is a benchmark of facial recognition pipelines and co-usability performances of modules. This is open access article, and in this article we identified that impact of alignment mode as 6%. I mean, if you disable the alignment mode, you would have 6% less accuracy. If you disable the detection step, its impact is 40%, 41%. And each facial recognition model and face detector combination gives you different accuracy scores. And in this article, we conducted more than 600 experiments, and I just shared a subset of these experiments. In the columns, you can see facial recognition models. In the rows, you can see face detectors, and this is run for L2 normalized Euclidean, and alignment is true. Meanwhile, this is tested on labeled faces in the wild data set, and we know that human beings have 97.5% score to verify faces on that data set. But you can see some cells are higher scores. For example, if you are using FaceNet 512 and retina face pair, we are going to have 97.4% accuracy. It's higher than human beings. And this is not just the only configuration. We have many configurations coming close to the human being accuracy or passing the human level accuracy. But some configurations, for example, DeepFace, consider the DeepFace column, they are very low when it's compared to human level accuracy. And these are the ROC curves of the best configurations of facial recognition models. You can see the perfect classifier with the bold red, and we are coming very close to the perfect classifier nowadays. To plot this ROC curve, we have to have the precision and recall scores, but we don't have the precision and recall scores for the human beings. We just have the accuracy score. That's why we cannot plot the human beings ROC curve here, but it's most probably located below this blue line and greater than this yellow line, because in the yellow line we know accuracy score is less than the human being accuracy. What I want to say, facial recognition research is almost done because we passed the human level accuracy already. Nowadays, our research interests are mainly focusing on the vector search on large data sets. You can see vector database posts in LinkedIn a lot nowadays because that's the research of today. If you want to search a face in a billion level database, how long does it take to find that face? I want to focus on that part of the research, what we are focusing on today. I mentioned face verification, and suppose that we are working in a bank and all customers have facial photos, and we want to use an authentication layer. And when you feed an image, you know the identity of that customer, and you don't have to search that customer's face in your database. You can access that customer's facial photo directly, and you need to compare it to take an image from webcam that time. We can describe the complexity of this task is O1. I suppose that the representation for this image in the database is already calculated. Actually, OD and D is the number of dimensions, but we can discard it. We can say O1, it's very fast. But if you want to search a face in a database, in that case, your complexity is going to be ON, and here N is the number of identities in your database. And again, I suppose that all vector embeddings for your facial database is pre-calculated. Calculation time of the vector embeddings is not considered in the search. Here, if your database is consisting of maybe 10,000, then it's okay, you can find the search identity very fast. If it's 100,000, still you can find it very fast, but what if it's billion level? In that case, vector databases or vector indexes play important role because they are running different algorithms for searching. If your database is small, you can still use DeepFace's out-of-the-box find function, and all you need to set is target image exact path, here angelina.jpg, and we are going to search this image's identity from database path. And I stored the images of my facial database in this folder. This is going to return a pandas data frame, so you can find it very fast if your database size is small. But it's not small. You have to do something different. You should use DeepFace's represent function, and this function is responsible for generating vector embeddings. And once you have the embeddings, you should store them in a vector index or vector database. And here I want to talk about how vector databases are working. They may adopt different algorithms, but the idea is going to be similar. And this approach retrieved from the principle from Spotify's Annoy vector index. Suppose that we have many vectors. Here we use two-dimensional vectors because it's easy to visualize. But in reality, we have multi-dimensional vectors. And again, for example, FaceNet uses 128-dimensional vectors. So it's impossible to visualize. But suppose that we have two-dimensional vectors here, and the red point is the target vector, and you want to find the closest, nearest vectors for this one. And the blue ones are highlighted as nearest ones because it's easy if visualized already. But in reality, how this can be done? We have the vectors in our database. Here, each X marker can be, for example, a song from Spotify, and you want to find or a playlist from Spotify. It can be anything. If you want to find a given vector from your existing embeddings, you need to build an index, and this is how vector databases running. Here, you need to first find the two random points, and the random points are highlighted with red markers here. Once you find your random points, you should find the equidistant line with respect to those random points. And here the equation of that red line is highlighted. And we are going to put this equation into a binary tree. We are going to put this to binary tree's root node, and we are going to separate all vectors into this line with respect to the being left or being right. When I put the decision node this line, thereafter I'm going to put all those vectors to the left branch and all of those vectors to the right branch. And in second level, I just have this vectors in the left branch, and here I'm going to choose a random 2 points again, here and here. Those random points are highlighted with red. Thereafter, I'm going to find the equidistant line again, and in the second level, I'm going to put the equation of this red line and split all vectors, this area and this area, to the left or right branch with respect to the being left or right. Similarly, I'm going to do this recursively again and again until I find 3 or 5 different vectors in the left or right branch, and I jumped the final stage. As you can see, this is going to like a spider web, and basically we are going to have a decision tree. It's going to be a binary tree, and each decision node will store a equation, lines equation, and we put all vectors to its branches. Once we calculated this, suppose that Spotify built this decision tree for its all songs. Thereafter, when a new song is given, you can find its nearest songs from this pre-built tree. How? For example, this is the path. You don't have to search the nearest songs of that given song from your all database, because your database is consisting of billions of songs. Instead of that, you can reach the nearest ones in 5 steps. It's going to be very fast. No matter what the size of your database is, you can reach the result in milliseconds, even if you have billions level database. Of course, you have to spend some time to build that decision tree, but this is going to increase the space complexity, but it's going to decrease the time complexity dramatically. Here, I put the link of Jupyter Notebook of that study, and I implemented this vector indexing from scratch. You can perform it by yourself. And as I mentioned, facial recognition research is coming to the end because we already passed the human level accuracy, but this is today's challenge. Nowadays, all vector databases are trying to offer a faster way to search. As I mentioned, this is a noise way to vector search. In the past, we know that Spotify was using this approach, but nowadays they announced that they are using Spotify Voyager, and it's a graph-based approach instead of tree-based approach, and that graph-based approach is 10 times faster than this tree-based approach, and it's still improving. So in this talk, I try to focus on the facial recognition technology, what we done in the past and what the researchers are focusing on nowadays. I thank you all for listening. As I mentioned, you can reach out to me from my personal blog or my Twitter address. I think we have 5 more minutes. If you have questions, I will be happy to answer. Thank you.